Hey guys, I am Naveen Sharma and I welcome you all to my YouTube channel, The Physicist Naveen. And today we are going to start the discussion of the topic, which is square well potentials, okay, which is in the continuation with the topic which we left previously in previous video. So today's topic is square well potentials, okay. So we will deal with the square well potentials. We will discuss what are square well potentials, and then we will see that in regions where the energy value is higher than the potential and in regions where energy value is lower than the potential, how can Schrodinger equation be solved and how can Schrodinger equations solutions can be interpreted in those regions. Now this discussion will be very useful when we'll be discussing step potentials, infinite square well and rectangular barrier potentials, okay. So this is a very important video for these discussions. So let me start by talking about what are square well potentials, okay. So these square well potentials somehow look like this kind of shape, because we also can call them some piecewise constant potential, because there is some discontinuity at some point in the we are discussing one-dimensional case here. So on the x-axis there is some kind of discontinuity. Let's say we divide this in three regions. This is region 1, this is region 2, and this is region 3, okay. And this here is the potential, okay. This is your v of x. So now you can see you have three regions, okay. This is minus infinite to, let's say, some value of a, okay. This is a and this is b, and this is from a to b, and region 3 belongs to b to infinite, okay. So you have three regions, three potential values. You can give them v1, v2 and v3 values, okay. So this is your square well potential, that is in one dimension. What is happening is, as you move along the one particular direction, you have one potential value, then you have a discontinuity, then you have another potential value in another region, then you have another discontinuity, and then you have another value. And this might keep on going, the potentials might keep on changing, but this nature of potential here is known as the square well potentials, okay. And basically what it does is it divides this one-dimensional region or one-dimensional space into some particular regions. For example, here three regions can be seen: r1, r2 and r3, okay. So here these three particular regions are being seen, and now these regions can have Schrodinger equations based on the energy value. So for example, you take a particle, let me change the color. So for example, you take a particle and a particle is moving in this region, okay. Now this particle moving in this region might have an energy value which can be greater than v1 or which can be less than v1, okay. And then depending on that what particle energy is compared to the respective potential in that region, the Schrodinger equation can be solved, and then the suitable boundary conditions can be applied for the solutions, okay. Now I am not going to solve the Schrodinger's equation here because that is not our goal, okay. If you want the Schrodinger's equation solution, these are in my notes, and I upload my notes in my telegram telegram channel. You can get from there the solutions of the Schrodinger equation, but here only the general discussion of the concepts is being done. General concepts are being discussed and problem solving techniques are being developed, okay. So for those theoretical proof, we are not going to delve into these videos, okay. So moving ahead, I told you about square well potential. I told you about how the Schrodinger equation in different regions can be solved. So now let's discuss about the first case, okay. I'm going to divide it into case scenarios. We will be having two cases. The first case is if the energy of the particle is greater than the value of the potential in a particular region, okay. So for example, here we had three regions now. So let's say that the energy is greater than the potential in any particular region, okay. Any particular region of any particular square well potential form. So now what we may have is, so for example, you know what is the Schrodinger equation, that is minus of h ket square by 2m and d2 xi over dx square in one dimension I'm writing obviously, plus you have the potential, then you have xi of x, then you have the energy, and then you have xi of x. Okay, now this is time independent Schrodinger equation. I have not written time dependent. Okay, so now you can transform this, okay, taking some multiplication and division, and then this equation basically reduces to d2 xi over dx square and plus of 2m over h cut square. Then you have E minus V of x. Remember, this potential is x dependent here. Okay, then you have xi, because this is changing form as you go from one region to another. As you go from one region to another, your potential is changing form. That's why it is x dependent. Okay, here, and then it is equal to 0. Okay, so this is your basically the Schrodinger equation. Okay, for any particular region you may talk. Okay, now what happens is this, you see here, this is the, let's say this is k square. Okay, so you know ordinary differential equations, second order ordinary differential equations, and how to solve them. So this is one kind of ordinary differential equation where this is xi double dash of x plus k square xi of x is equal to 0. This is one kind of a second order differential equation. So you know how to solve it. So now a general discussion which I want to do is this k square is a positive value here. Okay, because you see I took the case of energy to be greater than potential, and if energy is greater than potential, then this k square is a positive value. Therefore the k has a, this k also, if you check the dimensions also from this, if you compare, this xi is not included in k square obviously. From this, if you compare, this k has the dimension of the propagation constant. Okay, so if you see, this k will have dimension of propagation constant. Okay, that is a task I leave up to you. You can compare easily this. Okay, because that there is an energy, and then you take the square root, and there is the h cut, and there is a mass. So you will do that, and you will find that the k has a dimension of propagation constant. So if k square would have been negative, what would happen is, if the k square would have been negative, then it implies that k will be purely imaginary. Okay, the k will be purely imaginary. Purely imaginary, and that is not acceptable. Okay, not acceptable. Okay, that purely imaginary k is purely not acceptable, because this k has a dimension of propagation constant, and your propagation constant, I believe it cannot be, you cannot take that to be imaginary thing. Okay, your propagation constant needs to be a real thing. So going ahead with that, now as you see that your k square is positive and your Schrodinger equation basically reduces to this, you know how to solve it and what solutions are of these equations. So the solution of these equations resembles the exponentially increasing and exponentially decaying functions. So we can write them in the sine and cosine form. So xi x becomes some constant sine of kx and plus some another constant cos of kx, where k has the value of square root of this thing. Okay, so this was one case, one scenario. Okay, we discussed this thing. Now we have an okay, let me write the k square for you, that so that you might just not get confused in a better form. 2m e minus vx, just the above thing I'm writing here, nothing else, divide by h cut square. So this is your k square value I've written here, and now this is the case 1. We are done with it. Now I'm going to go on the case 2. Okay, remember, if you want the solution of this Schrodinger equation, you can refer to my Telegram channel. The link to the Telegram channel is given in the description box. Okay, and in-depth analysis and in-depth the solution of the Schrodinger equation has been provided there. Also, don't forget to subscribe the channel and like the video and share the video to all those students who are preparing for IIT JAM, GET and CSIR NET exams, physics exams. These videos might be helpful to them. Thank you. So the second case is the energy is less than the potential value. Potential obviously dependent on x, so I'm not writing it explicitly here. So if the energy of the particle in some particular region is less than the potential in some particular region, okay, in some particular region, we will be discussing problems also on these, okay. But before that, let's go on to okay, now remember the Schrodinger equation we wrote here, okay. This is very important, okay. Now here E minus Vx was the thing which we did and which made the k square to be a positive thing, okay. But if we go by this equation here, then the k square will be negative and the k will be purely imaginary, which is not acceptable. So what mathematical trick we can do here is we will write it as d2 psi over dx square, and we will take a minus common, which will make it to be something like 2m over h cut square, and it will become maybe vx of minus e, okay. V of x minus e of xi is equal to 0. This Schrodinger equation, now here we can take this as k square, okay. So it becomes to be xi double dash minus k square xi equal to 0. Very simple equation to solve, okay. And even still you don't know how to solve it, you can refer to the notes in the Telegram channel, okay. So the solution of this equation now will be of exponential functions such as a e to the power of kx plus b e to the power of minus kx, okay. This is the solution in some another region, okay. And the k square value, I can write it simply to be 2m over h cut square, and it will be v of x minus e, okay. So that is the kind of difference between these. Now a very quick example, and with this quick example I will be concluding today's video, okay. And the questions I will take a different session, that will be a long video, okay, 45-minute to 1 hour video. In that I will completely discuss all the problems related to one dimension, okay. But before that I want to complete all the one dimension topics, theoretical topics, okay. So quick example here, okay. Let's say we have a potential of such form, okay. This is one region, then we have this to be another region, okay. Of some form we have a, b, this is v1, this is v2, and this is v3. We have three regions, okay. And for example, now is the example starting this r1, okay. Let me tell that in this r1 vx is v1, and I'm telling you that my energy is less than vx, okay. Now what if my energy is less than vx? Then you know that the xi1x will be what? e to the power k1x, k1 because I am writing in the region 1, okay, plus b e to the power minus k1x. Now you don't need to directly solve now, because you know the results directly, that if the energy is less than potential value in some region, this is the form of wave function which your particle will follow, okay. So this is the value of xi1, and k1 square will be just 2m over h cut square. And remember, your k1 square needs to be positive, so v1 minus e, that you can follow. Now in region r2, let me write with a different color. Now in region r2 your vx is v2, and let me tell you that the energy is greater than v2, okay. So it's like here particle was following some energy, here it is greater, okay. So it's something like that, okay. So if energy is greater than v2, now you know what your xi2x will be. It will be some c sine of k2x plus d cos of k2x, where your k2 square, which obviously needs to be positive, so 2m over h cut square e minus v2, okay. Similarly for third region you can write now whatever energy value might be. It might be greater than v3, it might be less than v3. Based on that, like this or like this you can write, okay. It was a very simple thing to do, okay. Now based on this, direct questions has been asked in TIFR and JAM and GATE exams, so you might now solve the problem based on these. So these notes will be available in my Telegram channel, so go and join the Telegram channel. Also don't forget to like, subscribe and share the video and press the bell icon. Okay, thank you everybody, thank you so much. This is Naveen Sharma from Physicist Naveen.